Okay, so hello everyone. Welcome to this first problem solving session of this course, Introduction to Galois Theory. So I am Siddhartha Pramanik. I am a PhD student at IIT Kharagpur. Uh, so let's first summarize the topics of the first week. So meanwhile, if you have any doubt regarding the contents of the first week, you can ask by unmuting yourself by or by putting the question in the chat box. So the first
Hello, can you hear me?
hello.
Hi, can you hear me?
Yes.
I had a kind of a general question about the course, if that's okay.
You have what is your question?
So the thing is, I've taken a course in group theory properly, but I've only self-studied rings and fields. So I haven't done it as rigorously.
Yeah. So
So is it
yeah, it is okay. So
all the
no, not all things
subjects that
from
have
the
been
group.
mentioned? Do I need a... Sorry.
No. From the group theory course, not all the things we need. So basically, we need some things, and most of the things will be recalled when we will use those things. Okay.
Okay, so I don't need a very rigorous understanding of rings.
No, not all the things are needed. Some theorems might be needed, and most of the theorems actually we have recalled in the first week. So if you
Okay,
have
so only those are enough.
understand the statement, then that is also fine.
Okay. Thank you.
Yeah. Okay. Okay. So I will just summarize the contents of the first week. Then I will solve some more problems which will help you to solve the assignment problems. Hope that is fine. And meanwhile, if you have doubts, so you just unmute yourself and ask the doubt. So first week, sorry. Okay, I think we can start now. Okay, so in the first week, we have basically recalled some theorems of group theory and ring theory and some basics of field theory. So I will just summarize the topics. So it will not take much long. Then I will start solving problems based on those topics only. So let's start with the things. So in the first lecture, we just have summarized the overview of the course. So this is about Galois theory. So what is about Galois theory and what we are going to do in this course? So motivation for Galois theory. So that is what we have done. So this basically connects group theory and field theory, and as an application, we will see insolvability of quintings and some other things. So those are the contents of this course. So this is about the first lecture, and the second lecture is about recalling group theory. So in that part, so we have basically recalled the basic definitions of the group theory that we might need, and some famous theorems. So I will just list those theorems. You can go back to the video and again see them if you want. So we can start with the Callis theorem, for finite groups, and the Lagrange's theorem, and also the Cauchy's theorem, and the important theorem is Solo's theorems. So if you just have understood the statements, that is also fine. You don't need to see the proofs of all those things because we don't need the proofs in this course. And the final one is simplicity of the alternating groups. So simplicity of an. So this is for n greater equals to 5. So we have seen this mainly these theorems in the group theory. Then we move on to the ring theory part. And ring theory part we have basically started with the we start uh, yes. So review of ring theory. So we started with basic definitions. Then we move on to the other topics like ideals and different type of ideals, like which we are needed, that is prime ideals and maximal ideals. Then after that we have done the special type of rings, which are basically UFDs, PIDs, and then we mainly need the irreducibility criteria that we are going to use. So irreducibility criterions. So basically, we need to check when polynomials are irreducible. That is what we are going to use. So for that, some specific tools we have mentioned, like Eisenstein's criteria. So in the problems, I will do some problems based on these things. So if you have forgotten this criteria, don't worry, I will recall this thing also. Then the mod p irreducibility criteria. And I think this is all we have done in the ring theory part. Then we have done also some basic field theory. So in the field theory part, we have done several important things that we will use heavily in this course. So if you have got stuck somewhere in that part, you should ask and clear your doubt because that part is important. So mainly we have done splitting fields. So splitting fields And after that, so splitting fields exist and it's unique. Those things are also there. Then we have complete description for finite fields. So that is the structure theorem of finite fields. So structure theorem of finite fields. So this is a big theorem. So which states that for every prime power there exists a finite field and that is unique. So existence and uniqueness and how these fields are looks like. So these are splitting fields and when a finite field contained in another finite field, those things are there. Next, the algebraically closed fields and algebraic closures. So algebraic closures and algebraically closed fields. And the last part are the important ones, the extension theorems. So we have done two extension theorems. So both we are going to use in this course. So there is first extension theorem and second extension theorem. And also as consequence of extension theorems, we have proved two things. First one is this splitting field, it is unique. So uniqueness of splitting field we have done using extension theorems. And also the uniqueness of algebraic closure, that is also we have proved using extension theorem. So consequences of extension theorems. Okay, so these are the uh, this is the rough summary of the contents of the first week. So I will do problems on each of this topic so that you can recall the topics one more time. So first we will start with some problems from the group theory part. Then we will move on to the ring theory part. So basically we will do some problems based on these theorems of group theory. So let's see. Okay, so first let me write down the problem, then I will explain you the problem. So choose the correct statements. So so we have to choose the correct statements from the following ones. So first one is if G is a group of order 1000 and let and H is a subgroup uh, of G uh, okay of G such that order of H is bigger than 300, then H is normal in G. So this is the first statement. The second one is, if G is a group of order 8, so G is a finite group whose order is 8, then every subgroup of G is normal in G. So this is the second one. So third one is, if G is a group of order 9, then it has a normal subgroup, G is a group of order 8 too. Then it has a normal subgroup of order 9. Uh, let's see the fourth one. So if G is a group of order 81, then G contains an element of order 27. Then G contains an element of order 27. So these are the four statements, and we need to pick the correct one. So let's check one by one which one is true and which one is false. So you just take few seconds. So so that you can try on your own, and if you can guess the answer, then it's good. Then I will come to the answer. So first, let's try the first statement. So if G is a group of order 1000 and H is a subgroup of order bigger than 300, then H must be normal in G. So is it true or false? So so to check a subgroup is normal or not, there are several ways, right? So you can just follow that properties of normal subgroups. Okay, it's true. Can you say why it is true?
Order of subgroup will divide the order of group. So if order of subgroup is bigger than 300, then it has to be 500.
Uh,
And
is it necessarily of 500? So you are in
bigger
the
than,
correct way.
if it is 500, then it is normal because of index 2. But uh,
Yes. Yeah, you are correct, but there is some triviality you are ignoring. So order is bigger than 300, and by Lagrange's theorem, order of H must divide the order of the group, so which is 1000. So the only possibility is 500 and 1000. So if order is 1000, then it is the whole group, so it has to be normal. And if the order is 500, then the index is 2. Then also it is normal. So the statement is true. So just let me write down what I have said. So the first statement is yeah. So first statement is true. So it is just a consequence of Lagrange's theorem. So since order of h is bigger than 300 and by Lagrange's theorem, so what Lagrange's theorem says that okay, let me write down here. So if G is a group such that order of G is finite and if H is a subgroup, so then order of H must divides order of G. So this is the Lagrange's theorem. So by Lagrange's theorem, order of H must divide, sorry, order of H must divide order of G, which is 1000. So from that, we have only two choice, which is either 500 or 1000. So if order of H is 1000, then H must be equals to G. And if order of H is 500, then this index of H in G, this is basically order of G by order of H. So this is also, so this part is also follows from Lagrange's theorem. So this is basically 2. And we know that index 2 subgroups are always normal. So this is a simple exercise in group theory. You can recall it or you can go back to your group theory course. So in these both cases, H is normal in G. Okay, so I hope this is clear because nothing much we are using here.
Uh, Excuse me, sir. Like, hello.
Yes.
Group theory, most of the things. So, in my graduation time, I have not understood the parts, like what it's talking about. General property of group, though I know, and
Okay.
but when we go in the depth, na, so I face little bit problem. Like where, here just now, what is the normal subgroup and this all. So, should I go with the group theory course first, and then I come to Galois theory?
So have you seen the first week lectures of this course?
No, that I've seen, but I think in that also just the intro part is there, like basic recalling part is there, not matlab ki,
Yeah, so
maybe,
actually, for this course, the prerequisites are the group theory course and the ring theory course, and some linear algebra is also needed.
okay, okay. Linear algebra, though I'm comfortable, sir.
Yeah,
And
so
I,
you
I
can
have
go back to the
taken
group theory
this.
course, so it
Okay,
will be helpful for you.
so first of all, I should go with the group theory course. No?
Yeah, definitely, because this course is all about connecting group theory and field theory.
Okay. Otherwise, I'll be not able to understand a single line of this.
Yeah,
No.
many things in many places we need group theory, and in the applications part, in solvability of
Yeah,
questions.
yeah,
In
yeah.
that part we need solvable groups, so we will do
Mhm.
solvable groups in this course itself, but basic group theory is needed, so we will recommend
Okay,
you to go back to that course.
okay. Thank you, sir. Thank you.
Yeah, okay. Yeah, any other doubts? Okay, so the first statement is correct. What about the second one? So if G is a group of order 8, then every subgroup of G is normal in G. So is it true or can we get a counter example. Is it really a true? So why it is true?
So if group has order 8, group of order 8 is either Z2 cross Z2 cross Z2 or Z2 cross Z4. If it is abelian, then of course it is normal. So all subgroups are normal.
But
If it is
we are not.
non-abelian, then only case is, if it is non-abelian, then it is Q8, right? So
Yeah,
the only
Q8, or
subgroups
it
are,
can be the general group of on four vertices.
okay, okay. I'm sorry. If it is Q8, then all the subgroups are normal. But yeah, I'm sorry.
But what happens if it is D4, diagonal group of order 8?
Then the subgroups are, one is Z4, I mean isomorphic to Z4, and other are ordered two subgroups.
Yeah, so basically, if you take D4, then this statement is not true. So that will give you a
Okay.
counter example. Why? Let me come to that. So this is not difficult at all. So let's first write down the D4, how it's look like. So D4, so it's basically the symmetries of this square, right? So I hope you are aware of this group. So let me write down the elements. So here we have identity. So these are the four vertices. So if you rotate this square by 90 degree, so you will get the same square, right? But with the different vertices. So let me write down R90, which is rotation of 90 degree. Then R 180 degree, and then R 270 degree. These are all the rotational symmetries. But there are also reflections, right? So like if you reflex it across these diagonals, and also you can reflex it towards these things, so you will get four reflectional symmetry. So mm, so the around this first diagonal, let me write down as D1. Around the other diagonal, let me write down as D2. And around this horizontal line, if we reflex it, so I'll write down it as H, and other one the vertical. So we can write this group like this, but using the generators and relations, we can also write this as identity R square, RQ. And if you take just one reflection, and any reflection of the four, just take F, then FR square, FRQ, right? So I hope you know these things. So then this is the group of order 8. So here R is basically R90, and if you can take any reflection, and there is one relation also. So I should mention this, which is if RF equals to the inverse of R, which is RQ. So maybe I can write down it as if R equals to RFQ. Okay, it's FRF RQ. Mm, So this relation. So I should write it, I think here. So using this thing, you can completely uh, determine this group D4. This is the generators and relations. So one can see that this is cyclic group of order 4, and reflections has always order 2, right? Because if you take a reflection and if you just do the same move again, you will get the identity. So the subgroups are, so the subgroups of D4 are, so can you mention what are the subgroups using this information one by one?
Yeah, identity group.
Yeah, so let me list down the trivial one first. So identity and D4 are the trivial ones. Others?
And identity R square and R cube, subgroup generated by
Yeah,
R.
yeah, the rotational symmetries. So, okay, let me just write down the group subgroup generated by R. Yeah, any other?
Uh, Subgroup generated by F.
So you can take the, so it's a cyclic group of order 4, right? This part. So it has a order 2 subgroup also. So which is generated by R square. And all the reflections are have order 2. So you can take the subgroup generated by those elements also. So identity comma, okay, it's identity comma F, identity comma F R, uh, identity comma F R square, identity comma F R Q. So any other order 2 element? I think no. I think these are the all subgroups of D4. So how many? Let's count. Here are 4. Here are also 4, 8. So I think we have 8 subgroups. So among
So
these,
if we take any two elements and generate the subgroup, then it has to be D4, right? Means if we
if,
take
if we took
uh,
took any 2 elements,
two elements, means if I take R and F or FR,
yeah,
then subgroup generated by these two elements
yeah, definitely.
is D4. Right? So can we say in terms of like this spans D4, is there any terminology like that? Like
So,
R
sorry,
and
I
F
did not understand
spans.
you.
Uh,
Can you repeat?
I mean, like a subgroup generated by R and F.
Yeah.
Subgroup generated by R and F is D4. If it is
Mhm.
D4, then can we say R and F spans D4? Like in linear algebra, we say spanning set. Is that any
No, here
terminology like that?
how you will define spanning. So that is a different notion, right?
Okay.
So here in vector spaces, the scalars are coming from a field, but here we have only one object, one algebraic object, only the group. Okay. So here basically, which are the normal subgroups? Clearly, the identity and D4 are normal, and this subgroup generated by R means this rotational symmetry. It has order 4. So that means its index is 2. So it is again normal. Now what about the subgroup generated by R square? So you can check that this subgroup is also normal because this actually sits inside the center of D4. So that is uh, that is not very trivial, but you can check that. But if you uh, if you took these subgroups, these 4 subgroups, these are non-normal subgroups. That also you can check by direct computations by using the definition of normal subgroups. So D4 has subgroups which has a non-normal subgroup. So this statement is definitely false.
So just checking, like
हाँ,
these, in other words, can we say these four subgroups cannot be behave like zero in some question, like in D4. Like normal subgroup definition comes from like when n is normal subgroup in G, then n behaves like zero in G mod n, right? So
yeah, if n is
means
normal
these
subgroup,
sub
then only you
then
can define the quotient group G mod n,
question.
right? But if
So
it is not
G
normal,
mod n and so in G mod n behaves like zero. So this is not these subgroups are not normal. So that means in this set, these subgroups cannot behave like zero. Means we cannot define quotient groups. This
yeah,
is what is
these
conveyed.
are not normal,
Message.
so you cannot define the quotient group. That you can say.
Sir, one more doubt I had. Like in when we define D4, then we take the axis of symmetry is like a vertical reflection and horizontal reflection.
हाँ,
So the axis of symmetry these are. But
yes.
if in 3D if I say, then the same axis I can say it's a plane. I can take a reflection along that plane. But these two coincides in R2. The axis of symmetry like vertical axis is same as if I take plane and that reflect along this plane. In cube, if we take then the plane and vertical axis
No, no,
uh,
we are doing
are
in
two different things.
we are doing it in two dimensional, right? So if you go in three dimensional, then you have to consider cube. So in that case, things are little bit complicated than this.
But four elements only, sir. Sir, like four elements I have. Even if I take because in D while defining D4, it is not mentioned like dimension is not mentioned anywhere. So that is why
No,
like if I
actually,
take
yeah,
plane,
no, no, no. Actually, we can only consider rotations and reflection along these lines. That's the only thing, and we have to consider in two dimensional. In three dimensional, there are other objects also. So cube is
but
there,
it doesn't
tetrahedron
show
are
any
there.
contradiction. Even if I take plane, that coincides with one of these reflections only. So nothing new comes up. So I think that might be a reason they do not mention dimension. Even if I take this object with four vertex, all the
Yes.
three-dimensional symmetries if I take, these are
Okay.
the only possible symmetries because the other symmetries coincides with these symmetries.
Yeah, that is
So
true.
if that
But
so
if you
if I have
increase the
gate vortices, if I
dimension,
take cube,
things, yeah, it's
then it
true.
is
But
different.
if you increase the dimension, things will become little bit complicated. Na? That's why we are doing in two dimensions.
Okay.
There are other things we consider in three dimensions. There are in the books. So if you are interested, you can look in those things. But just now I am doing the second statement. So for that, this thing is sufficient. I think. Okay. Yeah. Okay. So let's see the third statement. So first one is true, second one is false. Now what about the third one? So if G is a group of order 18, then it has a normal subgroup of order 9. Is it always true or false? Uh, do you have any guesses or answers? The other participants, you can also uh, say your guesses or answers if you are comfortable. Because it's more of like a discussion session. Okay, so can you give any justification why it is true?
If I take the Silo first theorem,
Okay,
that it has a Silo group of order 9. Right?
yeah, and that has index 2. Yeah, definitely, you're correct. So we have to use the Silo's theorems. So that is the easiest way to do this problem. So this is true. So So by Silo's first theorem, so Silo's first theorem is all about existence of P subgroups. So Silo's first theorem, every group of order 18. So 18 basically 2 times 3 square. So we can take P equals to 2 or we can take P equals to 3. So by Silo's first theorem, every group of order 18 has a Silo 3 subgroup. And here the Silo 3 subgroup has order 3 square. So it has a Silo 3 subgroup of order 3 square, which is 9. So let's say, okay, order 9. And this subgroup has index 2, right? Because order is 9. So if you divide it by 18, then it's 2. And every index 2 subgroup is normal. Thus, it is normal. So there is nothing much to do in this statement. It's basically a consequence of Silo's first theorem. So I hope you can recall the Silo's theorems. If you are not able to recall, then you can you are feel free to ask it. Okay. So the third one is true. So what about the fourth one? So if G is a group of order 81, then it must contains an element of order 27. Is it true or false? So does every group of order 81 contains element of order 27? Yeah, any guesses? Okay. So why it is false?
If I take Z9 cross Z9, it has a maximum order of any element is 9.
Yes. So basically you can take Z9 cross Z9, or you can take Z3 cross Z3 cross Z3 cross Z3 and other groups also. So in these groups, you will not find an element of order 27. So it is also an easy exercise in group theory. So, uh, do you need any explanation or shall I skip this? If you are comfortable, then I can skip this because I need to cover the ring theory and field theory part also. So yeah, anyone? Mm, So maybe okay. Okay, maybe then we can skip the justification for this because it's not that much difficult. Okay, so let's move on to the ring theory part. So again, I will write down some statements and you have to pick the correct statements one by one. Okay, so the first one is so if you consider the ring Zi, the Gaussian rings of integers, and if you take the polynomial ring in one variable over this ring, then this is a PID, right? So let me write down Zi specifically. So this is basically A plus B times I, such that A and B are belongs to Z, and I means basically the iota, I square equals to -1. So first statement is Zi of X is a PID. And second one is let K be a field and if I is a prime ideal in the polynomial ring Kx, then I must be a principal ideal. So principal ideal means ideals which can be generated by a single element. So must be a principal ideal generated by an irreducible element. So I hope the second statement is understandable. Okay, the third one is, so the ring, so you take the polynomial ring over Z, polynomial ring in one variable over Z, and you go modulo by the elements 5 and x square plus 1. Then this ring is an integral domain. So we need to check this ring is an integral domain or not. This quotient ring. Okay, part D. So for every positive integer n, there exists a prime ideal, let's say generated by Fn, subset of the ring Qx. This is polynomial ring over the field of rational numbers. Prime ideal generated by Fn, where this degree of this polynomial Fn is exactly n. So let's look at these four statements. So let's start with the first one. So this is the polynomial ring over Zi. So we need to check it is PID or not. So what do we mean by PID? So a PID is basically an integral domain and second one is every ideal in this ring is principal ideal. All ideals are principal. All ideals can be generated by single element. So that is the definition of a PID. So is this ring a PID? Yeah, anyone? Okay, so why it is not a PID?
I feel like if I take ideal generated by x and 1, then any polynomial if I take with it has to be a single polynomial. If it is
Sorry, ideal
PID, then
generated
the
by
ideal
x
generated by
and
x and 1.
x and
1 if I
1.
take. Yeah.
So
No, no,
One is
one
basically
won't
a
work.
unit, right?
Unit. So two. If I take two,
Okay, so if you take
ideal then
comma 2,
x and two.
yeah,
Yeah, this might work because if it is PID, then the single polynomial should generate x and two. But if it
okay,
is, then fx should divide x and fx should divide 2, but then degree of fx has to be less than equal to 1.
okay.
So less than equal to 1 means it has to be equal to 1.
Yeah, so your approach is correct, but there is a slightly more direct way of doing this thing. So let me state that one. So yeah, you are true that it is false. So you can check this way. You can check in this way, like the ideal generated by x comma 2 is not principal ideal. That you can prove. But what I want to do is I want to give you a result. So let me write down as a proposition. So let R be a commutative ring with identity. Okay. Then uh, then if you take this polynomial ring Rx, okay, let me write down in this way. Okay, it is fine. Then Rx is a PID if and only if this coefficient ring R is a field. So this is one result that you can use here. So if Rx is a PID, then this R has to be a field. But in our case, what we have R is Zi. So we know that Zi is not a field because there are elements in this ring which are not unit. So as Zi is not a field, this polynomial ring cannot be a PID. So it's a simple consequence of that result. So if you have not seen this result, you can try to prove this. It's not difficult, or you may refer to the standard books. Or if you still not able to do, you can come back to me in the next tutorial season. I will help you to do this. So is it okay for the first statement?
So in general, the same, like if I take contrapositive A, if
Actually, your voice is very low. Can you?
hello.
Yes.
So in general, if I take ideal generated by x and some non-unit element, because if it is not field, then it cannot be PID. That is what the claim, right? The contrapositive statement.
Yes.
If it is not a field, then it cannot be PID.
So
So if it is
you
not a
want
field,
to
then it
want
has
to
to,
prove this result, or
yes, in general. So if it is not a field, then it has to be. It should not be a PID. So if I take the same example, ideal generated by x and some non-unit element, will that work? Like I haven't worked it out.
yeah, it might work. Yeah, I need to check, but yeah, it might
Because if
work.
it is not a field, then there has to be an element which is not unit.
Yeah. So
So
the
I
thing
can take.
is, if it's a field, then you can use the division algorithm to directly prove that it is a PID, right? So one side is very easy. It's a consequence of division algorithm. The other side, you have to use that trick. So you have to consider that ideal x comma some u to prove that.
Non-unit.
Yeah,
Yeah, non-unit.
yeah.
Yeah.
So you can try that, and you can work it out. And if you are not able to do, or maybe able to do, then you can let me know. We can discuss about it in the next tutorial.
Okay. Thank you.
Yeah, meanwhile, any other doubts or any other query before we move on to the next statement? Okay, so let's see the second one. So we are starting with a field K, and if I is a prime ideal in Kx, so I is a prime ideal in Kx, so then I must be a principal ideal generated by an irreducible element. So is it true or false? So if you use if you use this proposition, then Kx must be a PID, right? So every ideal is principal ideal, but is it generated by an irreducible element? So you are saying true, but is it true? Uh, yeah, think a little bit more. So what about others? Do you have any other answer? Yes, if prime is non-zero, then it is true. So in general, it is false. So it is false because we can take I is equals to the zero ideal because we are in an principal ideal domain. So in particular, it is an integral domain. Zero has to be a prime ideal. But it is true if I is non-zero. So this statement is very easy actually. Uh, so the first one is false. Second one is also false. What about the third one? So ZX quotient by ideal generated by 5 comma x square plus 1. Is it an integral domain? So the ring is the polynomial ring ZX, and ZX is not a principal ideal domain, that we also know. It is false. Why it is false?
So if I take difference of this x square plus 1 and 5, then x square minus 4 will
Okay.
belong to this ideal, but x minus 2 into x plus 2, these two polynomials are non-zero, but that product is 0 in that ideal.
Yeah. So these are non-zero elements, whose product is 0. Yeah, this is true. So it is not an integral domain. Yeah, you are correct. But we have a more convenient way of doing these things. So this is an observation. So x minus 2 times x plus 2. Okay, wait. Yeah, this is x square minus 4. This is basically x square plus 1 minus 5. So this is belongs to this ID. Okay, so this is one way. And but what we can do is, so this is an observation. So yeah, okay, so let me do what I want to do. So if you take this ring ZX mod 5 comma x square plus 1, so you can just go modulo by 5 first, then you can go modulo by x square plus 1, because these two elements are relatively prime, so you can do that. So if we go modulo by 5 first, then what we will get? So what is ZX module ideal generated by 5? Can you say what is this ring?
Z mod 5ZX.
Yeah. So this is basically Z mod 5Z of X, right? So we can write this as Z mod 5Z of X modulo by X square plus 1.
So, so you can write this because of these two are co-prime and use Chinese remainder theorem, right?
Uh, no, we don't need Chinese remainder theorem. You can directly write this.
The initial ideal is ideal generated by 5 and x square plus 1. You said
Yes,
this is same as if you can quotient 1 by 1. So
yes.
that is same
You
as
can quotient it by
z
5 first, or
अलग.
you can quotient it by x square plus 1, whichever way you
So,
want.
so
Okay.
we use the coprimeness. So that is what the Chinese remainder theorem says. Like
Yes.
z mod, you can write it as a product if it is their intersection is. No, I don't understand, sir. When can we write this?
No, no, no. This is not a product. Actually, we are taking sum of two ideals, right? Ideal generated by 5 plus ideal generated by x square plus 1. Chinese remainder says I1, I2. This is same as I1 intersection I2 because I1 and I2 are co-prime, and this is same as R mod I1 cross R mod I2, right? But here we are taking plus, not product, not intersection. So this is different.
So the second isomorphic theorem we used, like, can
Maybe
you
the
explain
third
this
one,
part?
I think.
What part?
Yeah, we are using the third isomorphism theorem. Okay.
Okay, got it.
Yeah. I is these two elements are co-prime. So if you take the image of x square plus 1 in the quotient ring Z mod 5 ZX, then these two elements actually are not changing much. That's why we can quotient it later. So that is the rough idea. But let's
But
not.
where have you used the coprimeness? The third isomorphic theorem is in general. Whenever two ideals are there,
Yeah,
some of
because
their ideals.
x square plus 1, sorry, 5 does not divide x square plus 1. So this element x square plus 1, it is not 0 in this quotient ring, right? So 5 does not
But
divide x
it
square.
doesn't.
Yes.
Anyway, we can write the above isomorphic statement that you wrote there. So
Yes.
that no contradiction there. Even if these two are not prime, we can write in this sense, right? Like
No,
if some
even
I and j are
if
there.
it is not co-prime, then I think we cannot write this.
But third isomorphic theorem doesn't say anything about coprimeness.
No, no, I am saying that if you go modulo by 5 first, then this, if you, now if this element becomes 0, then it is just Z mod 5 ZX, right? But these two things are definitely not isomorphic. Okay. Or you
So
can,
then there is something more with, then it is not third isomorphic theorem, there is something more
now
we are
we
using. Third
need third
isomorphic.
isomorphism theorem, not just third isomorphism theorem.
Okay. Can we write in terms of I and j, like the first one is I plus j, right? Idea. Ideal generated by 5 and x square plus 1 is ideal
No,
generated is I
I
plus j.
don't think we can generalize this. We need some more things. You
Okay,
cannot
sir, I'll
just do
try
it arbitrary I
next
and
time.
J.
Okay.
Yeah. So I think there is an example in the Artin's book, Michael Artin's algebra. This type of examples are there. So if you're interested, you can go there and see those examples. Is it okay? Yeah. Okay.
No, sir.
Yeah. So this is isomorphic. So we need to check this thing is a integral domain or not. Now, how to check this thing is integral domain or not? So this quotienting will be integral domain if and only if this ideal x square plus 1 is prime or not, right? So z mod 5zx modulo x square plus 1 is an integral domain if and only if x square plus 1 is prime. But is it a prime ideal in this quotient ring? Sorry, in this ring z mod 5zx? So we need to basically check, or we can write if and only if, because z mod 5zx is a PID, right? So it is if and only if is okay. So I'm messing up. If and only if x square plus 1 is prime. If and only if this ideal is prime, if and only if the generator is a prime element. And this is if and only if x square plus 1 is irreducible. Yeah. So now can you use the irreducibility tests?
That the last if and only if condition primes are irreducible. That if and only if when can be used? Like
So
what
why
condition?
this is if and only if you are
Yes.
saying? Yeah,
Yes.
Z mod 5ZX is a PID, right? So it is an UFD.
Okay. Okay. Clear, sir.
Or you can say that in a PID, a non-zero element, or sorry, a non-zero ideal I is prime if and only if it is maximal. You can use this statement also. So there are several ways of doing this thing. So this one might be the easier one. And an ideal is maximal in a PID if and only if it is generated by an irreducible. Yeah. So is it irreducible? How to check this one? So this is easier, right? Because it is of degree 2, and a degree 2 polynomial is irreducible if and only if it has a root. So so we need to check it is irreducible in Z mod 5ZX. So since so let's check x square plus 1 has root in Z mod 5Z or not. So Z mod 5Z is 0, 1, 2, 3 and 4. So you just check manually. So you will see that 2 is a root. 2 is a root. So this is actually 1 bar. 2 is a root of x square plus 1 bar. It is not irreducible. So as it is not irreducible, this ideal is not prime. Hence, this cannot be an integral domain. So I wanted to do this problem using this way because I want to bring this irreducibility thing. Otherwise, you can just directly observe this thing also. In this way, it is more easier to do. But this is also an way to tackle this kind of problems. Okay. So any doubts? So any doubts so far?
Sir, that isomorphism that we wrote, that Zx, mm, yes, Zx modulo 5 and the ideal generated by 5 and x square plus 1.
Yeah.
Consider this an I and j, I plus j, ideal generated by I plus j. So, say these two are co-prime, so then I plus j has to be equal to ij.
No, I
Co-maximal,
plus
sorry. These two
I.
are I plus j equal to ij because I and j are co-maximal.
Is it true? I don't think it is true. If I and J are co-prime or co-maximal,
Co-prime. Yeah.
what
Then
if?
it is true, right?
Then no, then I times J is same as the intersection, not the sum. This is not true.
Okay. Okay.
If I and J are co-prime, then I plus J will definitely be 1.
Okay, I'm sorry. This is one. Hmm. So left hand side is I plus j and right hand side we wrote it is same as quotienting one by one. R mod I first, then
So you are taking arbitrary ideal and I am taking just single principal ideals in this case, right? So that is also important. So this is a particular case and you are trying to generalize this. So that might not work. That is what I am saying. Maybe you can refer to those examples of RT. That will be useful for you. Okay. Any other questions or doubts? Okay. So the third statement is also not true. So definitely, since the first three are not true, so fourth one has to be true. But can you give a justification, proper justification why it is true? So the statement is for every positive integer n, there exists a prime ideal generated by Fn in the ring Qx, where this Fn has degree n. Yeah, anyone? So this statement, it is true. How we can do is by using the Eisenstein's criteria. So, so here the ring is Qx, right? So you take Fn just x to the power n minus 2. Then Fn is irreducible over Q. Why it is irreducible over Q? Just by using Eisenstein's criteria. So if you take the prime p equals to 2, so p divides the constant term, but p does not divide the leading term, and p square, which is 4, does not divide the constant term. So it has to be irreducible. So it is by Eisenstein's criteria. So the ideal generated by Fn must be maximal, and maximal ideals are prime ideal. So this result has to be true. Or you, in place of 2, you can take any prime number, because Eisenstein's criteria we just need prime elements. So you can do that. Okay. So let's. So do you have any doubts? Okay, so let's quickly do some problems in the irreducibility part. So which of the polynomials are irreducible? So are irreducible over f. So I will mention f, the field in each part. So the first one is x power 7 minus 9x square plus 3 over f is equals to q. The second one is okay. Let's do the first one. Then I will go to the second one. So can you say it is irreducible or not? So let me recall the Eisenstein's criteria because in the previous problem I have used it but I have not recalled. So let fx belongs to zx uh, be a non-constant polynomial, and suppose p be a prime number okay. I need to assume the f also, sorry. So let fx is n x power n plus dot dot a1x plus a naught belongs to zx be a non-constant polynomial. Then we want to check fx is if fx is irreducible. So we will give a sufficient condition. So suppose p is a prime number such that p divides a naught up to a n minus 1. P does not divides the leading coefficient n. The p square does not divide the constant term. Then f is irreducible over q. So this is the Eisenstein's criteria. So we need to find a prime number which divides all the coefficients except the leading term, and p square does not divide the constant term. Then this polynomial has to be irreducible over q. So that is the criteria. So if we use this, can we say this polynomial is irreducible over q or not? Yes, anyone?
It's irreducible.
Yeah, so just take p equals to 3 and use Eisenstein's criteria. So I hope you got this Eisenstein's criteria. It is not difficult. So it is just the applications of Eisenstein's criteria. Now what about the second one? So you take 2x cube minus 6x plus 5 over f equals to r. So is it irreducible? Anyone? So what is the definition of an irreducible element? An element A in a ring R is irreducible if the first thing is A is uh, non-zero and non-unit, and second thing is A cannot be written as some B times C, where B and C both are non-zero non-unit. So we cannot factor A as product of non-zero non-unit elements. That is the definition, right? So can we factor this polynomial over Rx? So definitely it is not irreducible.
Yes, it can be. If I take 2 out, 2 is a unit. So 2 is a unit.
So
So it's a degree 3 polynomial over R. So the in complex number there are two roots, 3 roots. So if I take those complex roots, those two heads to be conjugate. If I take those two pairs, and that will become a polynomial over R, and the remaining part
So
the
yes, you
factor
are in
in.
the correct way, but the justification is, so degree of this polynomial is odd. So it must have a real root. So if it has a real root x minus alpha, then that factor must divide this polynomial, right? So since degree is odd, so it must have a real root. So it must have a degree 1 factor, and so it has one degree 1 factor and the other one is degree 2 factor. So it can be written as product of two non-zero non-unit elements. So it is not irreducible. So I hope you got this. So let's do this one.
Very nice. ISIS 10 criteria in these three conditions. If the second condition doesn't hold, then clearly it is reproducible. Is this explanation right? If I take prime out, the prime and the remaining part. No, no, that. And I wanted to know a counter example where first and third condition holds, but second doesn't hold. Then it is reducible.
So reducible over Q.
Irreducible over Q. If P divides the leading coefficient,
Yes.
then is there what counter example will be?
Uh, so if you want to remove this condition, then what happens? So
Yeah,
definitely it
if
is
P
not
if for some
irreducible
prime,
over Z.
means I can't take common factor as P, right? Because other then I have to divide all other coefficients by P.
So most of the cases when we talk about Q, we basically look at monic polynomials, right? So in that case, the leading coefficient is always 1. So uh, so what happens if you take degree 2 polynomials? So if you take this polynomial, then what happens to its roots?
If I take 2 common out, then 2 times x square plus 2x plus 1. 2 is also irreducible, and
2x plus 1. So it is basically x plus 1 square, right?
no, even we don't have to do it. Even if that part doesn't factor, 2 is there, right? 2 is not unit in that. Okay, over z, over q here.
No, you want to remove the second condition, right? This one. So you need
Yeah, second condition.
p divides
But
the leading number.
here in the second part itself, does it imply that it is reducible? 2 is unit, so we cannot say, right, it is
2
reducible.
is prime number, right? We need prime over the base with z.
No,
Here p
this part
equals
is
to
okay,
2.
sir. P is equal to 2.
Yeah. So this polynomial is not irreducible over q. In fact, over z. So this will give you a counter example. Is it okay?
Yes, sir.
Okay. So let's look at this part C. So what about this? Is it irreducible?
No, 1 is root. So,
So as it is a degree 3 polynomial, you just need to check it as a root or not. So since degree is 3 and 1 bar, sorry, we need to take 1 bar is a root, so it is not irreducible. So this is fairly easy. So let's move on to these things and let's go to the field theory because I have not much time. I want to do some problems in field theory also. So meanwhile, do you have any other doubts or queries? Yeah, anyone, any doubts? So which of the following is true? So the first one is if you take pi, then pi is transcendental over q adjoint pi q. The second one is if alpha comma beta belongs to R are transcendental uh, over Q, then it will imply alpha plus beta. Okay, it will imply either alpha plus beta or the product alpha beta is transcendental over Q. The third one is you take the element 1 plus cube root of 5, then this has degree 3 over q. So I will explain the problems, but first let me write these problems. The fourth one is take the square root of 3 plus 2 times square root of 2. So this has degree 4 over q. So these are the four statements. We need to check which one is true and which one is false. So first one is about transcendental uh, over a field. So let me recall the. So it is false, you are saying. So first let me recall the definition of transcendental quickly. So suppose you have a field extension K over F. That means F and K both are fields and F is a subfield of K. So then an element, let's say alpha belongs to K, is algebraic if P of alpha equals to 0 for some uh, non-zero polynomial Px belongs to Fx. So an element alpha belongs to K is algebraic if alpha is a root of some non-zero polynomial over Fx. And if alpha is not algebraic, then we say it is transcendental. Maybe I can write here. And if alpha is algebraic over F, is not algebraic over F, then alpha is transcendental over F. So that is the definition. So I have written it very badly, but I think it is understandable. So what about the first one? Pi is transcendental over this field or not? So you are saying it is false, means pi should be algebraic over this field. So, uh, so can you give the polynomial of which pi is a root?
Uh, x cube minus pi cube.
Yeah, exactly. So take fx is equals to x cube minus pi cube. So this belongs to this polynomial ring, and okay, so this is a non-zero polynomial in this ring, and f of pi equals to 0. So this means pi is algebraic over q adjoint pi q. In fact, you can check that this is the irreducible polynomial of pi. That is also easy. So first one is false. So this one is fairly easier. So what about the second one? So here in the second one we are considering the extension R over Q. So we are taking alpha beta belongs to R. It is true. Okay, why it is true?
Let's consider the counterpositive statement. Like if this implies alpha plus beta and alpha beta are transcendental over Q, then suppose alpha beta and alpha, the negation of it is alpha plus beta and alpha beta has to be algebraic over Q.
So yeah, so
So
we want to prove that either alpha beta or alpha times beta transcend.
yeah,
Suppose
so
this is
negation
not
is
true.
both of them has to be algebraic.
Yeah, so suppose this is not true. That means both are algebraic. What happens?
Then sum of two algebraic elements is again algebraic. Then alpha
Yes,
minus beta has to be algebraic.
alpha minus beta.
Yeah, alpha minus beta can be written as alpha plus beta
Yeah,
whole square minus.
yeah. So yeah, you are in the correct way. Let me write down this. Suppose both alpha plus beta and alpha beta are algebraic. then what we will do is we will write alpha minus beta as you take alpha plus beta square and you subtract 4 times alpha beta and you just take the square root. So alpha plus beta and alpha beta are algebraic. So this element and this element is also algebraic. So this whole element is algebraic. So alpha minus beta is algebraic. So alpha plus beta and alpha minus beta are algebraic. So if you take sum, so 2 alpha is algebraic, but 2 is a real number which is also in Q, so you can just remove it. So alpha is algebraic, but this is contradiction because alpha is transcendental. So this has to be true. So is it okay for others? Okay. So if you have doubt, so please feel free to ask the doubt because it is an interactive session, so you can interact without any hesitation. So what about the third one? So what is degree of an element? So degree of an element means the degree of the minimal polynomial of that element. So write this. So suppose alpha belongs to K and K over a field extension. So alpha belongs to K is algebraic. Then degree of alpha is basically the degree of the irreducible polynomial of alpha over the base field, or the minimal polynomial we usually say. So that is the definition. And this is actually same as the degree of this extension. Okay. So because if alpha is algebraic, so this extension is finite and these two numbers are same. So what about degree of this element over the base field Q? Is it 3 or not? Yeah, any guesses? Yeah, anyone? Any answer? Okay. So let me do this. So here your alpha is 1 plus cube root of 5 and your base field f is q. So you want to find the degree of this. So we want to find degree of q adjoint 1 plus cube root of 5 over q. Right? Now uh, this thing is same as degree of cube root of 5 over q because these two fields are same. Why it is same? because this 1 itself belongs to Q, so it will absorb its own elements. So this is a basic exercise in field theory. You can prove this. So now can you say what is this degree?
Four.
Is it 4? What about the
Like we
degree?
need
We need the degree of
we
this
need a
element.
square root of 5 to
See,
3, an iota and minus iota will no
no, what
no
is
no no.
the degree of
Okay,
this
okay, okay.
element?
3.
Yeah, it is 3. So because if you take xq minus 5 belongs to qx, it is the minimal polynomial or irreducible polynomial over q. Why it is irreducible? So clearly cube root of 5 is a root of this, and it is irreducible by Eisenstein's criteria. So it has to be the minimal polynomial. And since it has degree 3, so degree of this extension is 3, which is same as the answer which we are looking.
So if we consider over R, then
If we consider over,
R, real numbers.
then it has to be 1, because this itself a real number. This is real cube root of 5.
Okay, okay.
Yeah. So basically the idea is to use this observation. The rest part is easy. So the third one is true. So I hope it is fine for you. So what about the fourth one? What about the degree of this element? So here alpha is square root of 3 plus 2 times root 2, and the base field is q. So can you find this degree of this element? Okay, so I think, okay, let me do this. So observe that. So basically we need to find the minimal polynomial of this element over q, right? Degree of that polynomial. So first we need to find that polynomial. So we can write this. So this is 1 plus 2 times root 2 plus root 2 square, right? So this is same as 1 plus root 2 square, and you take the square root. So this is basically 1 plus root 2. So now we need to find the degree of this element. So uh, degree of alpha over the base field q is same as degree of this field extension q adjoint square root of 3 plus 2 times square root of 2 over q, and this is same as the degree of q adjoint 1 plus root 2 over q. Now you play the same game. So this is same as degree of q adjoint square root of 2 over q. So 1 belongs to q, so it will absorb its own elements, and this is simply 2.
So, sir, whenever we take the square root, we mean on the positive part, right?
So you can take the negative one also, because
Okay, if
plus
root
and
2 is
minus
there,
it
then
will not
minus
matter
1.
here. So
But
if
in general, when we write square root, so we mean by only positive square root or
yeah,
the both.
we usually mean the positive part, right?
Okay.
But even if you pick the negative one, since it is a field, its negative should also belongs to this field, right? So what I am saying is q adjoint. So 1 plus root 2 is same as q adjoint minus of 1 plus root 2, because it's a field, so its additive inverse must also be in this field. So it does not matter here. Yeah. So is it fine for others? So this degree is 2, not 4. So this thing is false. Okay, so let's uh, let's do some more problems quickly, maybe the easier ones. So it was problem number 4. So the next is problem number 5. So it's true or false that no finite field is algebraically closed. So no finite field is algebraically closed. Is this statement true or false? So what do we mean by algebraically closed fields? So a field F is algebraically closed if every non-constant polynomial let's say fx in fx has a root in f. So we say a field f is algebraically closed if you take any non-constant polynomial fx over fx, then that polynomial has a root in f itself. If it is true for every non-constant polynomial, then the field is algebraically closed. So is it true for finite fields? So is the definition clear? So I think we have done basics of algebraically closed fields in the first week itself. So I hope it is clear. So this is true or false. Finite fields are algebraically closed or not. So finite fields actually never algebraically closed. So this is true. So why it is true? Let me prove this. So it is very easy. So let f be a finite field. So since it is a finite field, it has finitely many elements. So then, sorry, suppose f is some alpha 1 up to alpha n, right? Now consider the polynomial x minus alpha 1 dot dot x minus alpha n plus 1. Now this polynomial belongs to fx, and this polynomial has no root in f. Then if you evaluate f at any alpha I, you will basically get 1, which is not 0. So for all alpha 1 up to alpha n belongs to f. So f has no roots in f. So we have found a non-constant polynomial which has no root in f. So f cannot be algebraically closed. Okay, so this one is fairly easier. So if you have understood the definition clearly, then this would be clear for you. Okay, let's do one more problem, then maybe we can wind up. So finite fields are not algebraically closed, right? But in the lectures we have seen that every field has an algebraical closure. So if you take an arbitrary field f, then you will find a bigger field such that this extension is algebraic and this field k is algebraically closed, and we call this field uh, algebraic closure of f, right? And we denote it by f bar, and it is unique up to isomorphism. So algebraic closures exist and it is unique up to isomorphism. So for a finite field, can we uh, give a description for its algebraic closure? So let P be a prime number, then let's consider the field with p numbers, field of cardinality p. So this is one of the standard notations. So it is a field of cardinality p, a finite field of order p. Then show that, so you take the field of order p, and if you take this algebraic closure, this is same as you take the union of all finite fields of order p power n. So we need to prove this, that this union of fields is the algebraic closure of this fp. So so did you understood the question? So we need to prove that this right hand side is an algebraic closure of fp. So how to prove this one? So first of all, this right hand side has to be a field. Is it a field? So this is actually, you can use the definition of a field to check that it is a field. So clearly this union of fpn is a field, and it is, and okay, let's not and. So here we will use the structure theorem. So recall that if you take the field of p power m elements, then it will contain in the field of p power n elements if and only if m divides n. So this is one part of the structure theorem. I hope you can recall. And so this is first thing. And the second one is uh, so if p power n1 times n2 is a field containing both the fields fp power n1 and fp power n2. So this second part is follows from this first part, and using the second part you can prove that this union is a field. So this is one thing. Now why this is the algebraic closure? So union of fp power n is a field which contains all finite extensions of fp, and this union is also algebraic over fp. So thus it has to be the algebraic closure. Because you cannot extend it further to get an algebraic extension of fp. So that is why it is the algebraic closure. So maybe after going to the Galois theory part, this will be more clear, but I wanted to do it now.
But
So
why it is smallest, sir? Means
yeah,
it contains all finite extension.
sorry.
But
Hello,
this union
sorry.
F,
Yeah.
why it is smallest? Means
So
closure means it should it contains all finite extension. It is
yes.
algebraic over F.
So I
Fine.
want to say that you
But
cannot extend this further to get an algebraic extension of fp. So here you have fp, and here you have union of all fp power n, right? Now if you want to extend further, let's say so this part is algebraic. Suppose here you have some k which is also algebraic, and let's take this is proper subset of k. So you pick an element alpha belongs to k which is not
why we are
in.
considering the upper part like K? Why we are considering K already? F the union is algebraic over
Yes,
FP. Then
yes.
the algebraic closure has to be either this union or the smaller than that, right? The smallest part is the algebraic. Why we are going up?
So what do we want to prove here? We want to prove that this is the algebraic closure. So how you will prove that?
Close. Yeah. So this is algebraic over FP.
Yes.
So the algebraic closure is the smallest field which contains FP and it is algebraic, right?
But why
The
it is smallest in which sense? Smallest.
smallest means
So means you cannot
thing.
further extend it to an algebraic extension, right? So there are several equivalent conditions for an algebraically closed field. So, so I mean that you cannot further extend like this to get an algebraic extension of FP, right? So that is one thing. So in that way, you can prove that this is algebraic closure. Is it okay? Yeah. Any doubts? Yeah. So any doubts so far? So we have done lots of problem covering all the topics. Yeah. Any doubts or queries? Or maybe we can wind up because I'm already over time. Okay. Yeah, okay. So if you have no doubts, then maybe we can wind up today and we'll meet again in the next week. So bye, all of you.